our heroes, we had just realized why it was important to have things like this, the implications of them, right? They immediately give unique ergodicity if you have them for a rich enough set of x tilde, right? And I claimed that various properties like this are true if you force with very rough. Okay, so this is not very rough forcing. If P is 1 million, you know, that's like in Sobolev space 1 million or 1 million minus 1 or 1 million plus 1 or something. But it's not the same thing you get if you just forced with finite dimensional noise, right? Or if you force with analytic noise, right? Because we know that if you force with very smooth forcing, Navier-Stokes, for instance, kind of sets up to be Chevret analytic. It just decays exponentially. That's the best thing we can prove. Probably that's what's true, in fact. So let me talk about some of the tools that one uses to prove these type of things. So I'm going to talk about one set today, and then I'll start next time talking about a different perspective. So I want to talk about kind of the first one that you learn, which is the Cameron-Martin theorem. So to set that up, I'm going to look at this cylindrical Brownian motion. So it's just this formal sum of IID Brownian motions with some L2 basis, some basis of my, let's say this is a Hilbert space, yeah? And then I wanted to find some operator that takes these basis elements and takes them in some directions, all right? So QW is just the summation of directions, little q times WK. And now the question that's really useful to have is, well, when can I incorporate in a shift of the Brownian motion and that leaves it absolutely continuous, okay? So the celebrated Cameron-Martin theorem says that if you have like some deterministic function h of t, and if I define w tilde to be w plus this shifted function, and the log time t are equivalent if and only if this L2 norm, so I should have maybe put in L2 here. This L2 norm is finite, where this is what I need, okay? And whenever I write Q inverse, I'm in infinite dimensions, so I really mean the pseudo inverse, right? I mean because there's places where it's not invertible, so I only mean the inverse on the places where it makes sense, okay? All right, questions? So what, right, what does it mean to, so what that means is you can write this dw tilde time t as some on path space. There's some density, right? It just reweights the paths, right? And of course, if it just reweights the paths, let's just think about this in our minds for a second. If it just reweights the paths, that means it kind of follows the same path that it followed anyway, just with different weights. Now you have to think a little carefully about that because we're talking about paths in the continuum, right? So it's the same contradiction we have all the time that we're all used to, is that, pick a point uniformly in the interval 0, 1. If you pick any point and ask what's the probability of picking that, the answer is 0. But yet every time it picks a point. So it picks some point every time. So that's, a little bit of, you have to get your head around that. So the same thing, right? There's some set of continuous paths that W takes, and W tilde just chooses exactly the same set of paths with just different weights on them, yeah? And of course, think about what I just said about the ergodic theorem. If I pick some positive set of paths and I look at their time average, that's enough to determine what the properties of the measure, right? I can time average along those paths and get what my measure is integrated against the test function, yeah? So if I could show that like some paths are equivalent on infinite time, for instance, which is what I essentially did when I said they agreed at time t and then agreed from then on out, right? They had the same paths out at infinity. Then that would be enough to say that two property problems had to have the same asymptotic behavior, right? So there's some probability, right? So this can be very powerful, all right? Okay, so in particular, so here's what there was some prelude talk to before. So here I've written down two different sorry, I thought I had my. So here's a linear equation, yeah? This is a linear operator, and I have just some inhomogeneous forcing. And so this is a Gaussian, and I just took the initial condition to be 0 here for a second. By Duhamel's principle, or variation of constants, or linearity of linear superposition of linear equations, whatever your people call it, this is the solution of that equation, yeah? The stochastic convolution. Yeah? And of course, if I have some other forcing, if some other right here inside H, which is deterministic for a second, then of course the inhomogeneous force, the inhomogeneous equation is just given by this solution. Yeah. So if I now want to ask, do these two equations have the same, are absolutely continuous at time t, the densities they induce? That turns into asking about if this H tilde here, which is deterministic in this case, I've underlined it, whether this satisfies this bound. If I invert Q against H, is it an L2? Now, all of a sudden, you see why this thing I said about if you have too smooth of a Q, you're in trouble. If Q is very smooth, then I take the inverse of Q, and that's very rough. And now I have to apply it to H. So I have to know that H is super, super, super smooth, right? Now, of course, that's not unbelievable because somehow Q is what was setting the smoothness of, right? So there's some interplay here between the two. And the question is whether this H respects that interplay. If it does, you get absolute continuous. If it doesn't, you don't. So now, so here, of course, you know, we all the time in PDE theory apply Duhamel's principle, apply variation of constants, where this is some function of the solution itself, right? We write a weak formulation and we write a variation of constants formulation of a problem. But we need this to not be deterministic. We need it to be depending on the solution U, yeah? So we would be interested in an H of t where H actually depends on the randomness thus far. That's what it means to be adaptive. This means that it's measurable, that the value at time t can be determined by knowing all the randomness up to time t, right? That's what this means, it's sigma algebra generated, right? And so now if I define this process, then the Gersanov theorem, which in some sense follows, depending on how you prove it, from a Cameron-Martin theorem, it says that the law on path space, so if I start them from the same initial condition, so I'm starting them from 0, the law actually on paths 0t are equivalent. Okay, with a little bit of soup up, you can get equivalents, but they're at least absolutely continuous in one direction by if this is almost surely finite. You get a little more if you have some integrability conditions, if you know this kind of stuff, if you have Novikov's condition or Hasnitzky's condition, right? Then you can get some equivalence here, but you know, a simple stopping time argument gives you this. All right, so this gives you kind of equivalence on path space. And so now if we take this reaction diffusion equation, yeah, we take this reaction diffusion equation in 1D, we can actually prove that if I take the Gaussian measure here and the nonlinear equation here, then this becomes my H. I want to get rid of this H, right? I want to get rid of this equation. So we can actually prove that the law on paths of U is absolutely continuous with respect to the Gaussian measure. So of course, now if I want to know anything about this solution here, I could tell you about it by studying this solution. Almost sure properties. Like if you wanted to know what's the Hausdorff dimension of the zero crossing of this equation, it will have the same Hausdorff dimension as this one. I know that's confusing, isn't it? The Hausdorff dimension, not how often it does or things like that. Yeah. Oh, it's absolutely continuous. So yeah, so this is true. So you can prove this on path space. And the way you prove it is you just do this. You rewrite this as now I've just used Duhamel twice. So this is the stochastic convolution term. This is the nonlinearity. And now I've written Q inverse just like this. So now what I want to do is I want to make this into a new Brownian motion. Right? That's what Gersanov told me how to do. It said I can treat this as a new Brownian motion, W tilde, and thereby turn it into the same equation as the heat equation. Right? That's the idea. Yeah. And so if I can prove this estimate here, so this my H was those US minus US cubed. If I can prove this almost surely finite, then I get this absolute constant. Yeah. Okay. Questions? Yeah, Jessica.
Is there a way to see this as like a comparison principle? These two solutions?
No, it's actually just the opposite. So let me explain that. So I always say that kind of, so there's a group of people in the world that like to talk about, if you talk about a stochastic ordinary differential equation, they only like to talk about the densities, the PDEs, the Fokker-Planck equations, right? There's another group of people that only want to talk about, I wasn't trying to compete. There's one group of people, let's just call them, I don't know, Jacob. Give them a name. Then there's another group of people, I don't know, let's call them Alex. That really always want to think of it as a dynamical system, right? That always want to think of it strictly pathwise, right? But the thing that links questions about the paths and questions about the densities, about the probability, is Gersonov's theorem. So it's really a weak statement. It's not talking about an order, there's no ordering, there's no comparison, right? It's not a path by path statement about the SPD. Yeah, it's really a statement about the change of density when I average over a bunch of paths. So it does not induce an ordering to the best of my knowledge. There is reaction and fusion, is of course an ordering, and that's a different conversation. Like there's a whole bunch of cool things you can prove about this equation because you can use the ordering, the partial ordering on solution spaces, which I'm not invoking here. And there's a bunch of cool theorems about random attractors and stuff you can use because this has a partial ordering. What about burgers and KPZ? Okay, so you say, well, that was easy. Let's just do the same thing. So you say, okay, I want to get rid of this term here, right? I want to Gersonov away, as I like to say, make it a verb. Gersonov away this term. In other words, absorb this into this Wiener process, yeah? And just get the heat equation, right? And so an easy way, yeah, is that a question?
Yeah, sorry. Could you just, before moving on with that, could you give an idea for the earlier one as to how you actually show? Because it seems to me like in order to get you, right, because of the nonlinearity, you need to sort of solve some fixed point problem.
Yeah. So I'm assuming you've got equation, you've got solutions.
Great.
All is hunky-dory.
Fantastic.
And and then you have to go do some work. You have to say, like, I'm going to show some regularity of these
Okay,
solutions.
so
you have to do some regularity so that you can then do this estimates, right?
Awesome. Okay.
I'm skipping all that part.
Okay, great.
I'm skipping all the PV part. I'm about to do a little bit of it right now.
Okay.
I lied. Okay. I'm about to do it for you right now in an example.
Okay, great.
All right. So a standard trick in stochastic PDEs is to decompose the solution, in fact, into the linear equation and the remainder. All right. And if you do that, then Z satisfies this linear equation, and then V satisfies this random equation, yeah? And of course, if you think about it, you can expand out this, right? You can expand this out. This is V squared plus 2VZ plus Z squared, right? And if you think about it for a second, maybe kind of you might think like, well, the worst term certainly looks like this, because this equation here has this stochastic forcing term, where this one has Z, which is then hit again with this smoothing operator. Everything I'm saying is when you're using classical solutions. As soon as you get up to like regularity theory or singular SPDEs, what I'm saying right now is not true. We'll come back to that in a moment. But here for a second, when we have classical positive Sobolev regularity. So you look at this and you do a little work. And if you want me to, I can talk to. I couldn't talk about everything, but you can show that it has this regularity. That is to say, continuous in time with this Holder regularity in space. See, alpha is my power here, right? So when alpha becomes negative and this becomes smooth, this becomes higher Holder regularity. Yeah, everyone good? So if you want to like hang your hat on something, think of alpha less than 1/2. That's kind of what I'm thinking. Everything is hunky-dory, alpha less than 1/2. Alpha less than 0 is just glorious. Okay. Well, if alpha is less than 1/2, then this Holder regularity is positive, right? So then Z squared, the regularity of Z squared is also the same. It just gets the same regularity. And then there's a minus here if you're really for the cognoscenta. It's just minus epsilon, right? If Z squared has this regularity, then I take a derivative of it and I lose a derivative, right? I subtract 1. So now I have minus 1/2 there instead of plus 1/2, yeah? Then I hit it with, right now, what do I have to check? This is the object I have to check was an L2, yeah? So now I hit it with the minus of the Q, right? And Q was an alpha derivative, so now I have a minus alpha derivative. So that kills that alpha there, yeah? And now I end up with this regularity. So you're like, okay, I can't prove pathwise absolute continuity on path space, right? I can't prove this on path space. And I'm like, okay, but who cares about it on path space? I only cared about it on time t. Maybe that's easier to prove. So then you went back, you said, well, before you talked about this Cameron-Martin theorem. And if I look at this equation here, I have z just plus this term v of t. Can I just treat that as my h? And if you do that, you'll find out actually that then what would that differ? The difference between that and this was that this term would now have an integral and a semigroup, right? With two derivatives here. I'm going to wait till that goes away. I'd have an integral from 0 to time t with a semigroup here. And so I get some smoothing. And in fact, typically when you hit something with the semigroup generated by the Laplacian, you gain what? One derivative. Yeah, in L2. Yeah. So, well, that would be great. If I added a 1 to this, I'd be super happy. It'd be C1/2, right? The problem is that you need this to be deterministic to use Cameron-Martin like that. Look, who's just below the line. So there's that calculation I just talked you through abstractly. If I put in the heat semigroup and now did this, I would get this in C1/2, and I'd be happy. But it's not deterministic, so I can't use Cameron-Martin. So what I'm going to do is I'm going to think about Duhamel. And this certainly came out of thinking about various, I don't remember. I think a lot of the inspiration of this definitely came from reading some of Shumet's work. In fact, I've written out the solution to you, the variation of constants, right? If you're a PD person, this is the mild formulation, right? Here's my stochastic convolution. Here's my nonlinearity, where f is just, I'm just thinking of f right was dx u squared 1/2 for a second. Yeah, but I'm going to think about it just abstractly for a second, okay? So I'm going to do something that first looks like a trick, and then I'm going to draw a picture and explain to you why it's not a trick. It has intellectual content. I'm going to take this time integral and I'm going to split it into two applications of the semigroup. That's what it means to be a semigroup. And now I'm going to change time. If I change time, you can trust me that I change the integration from t/2 to t. I get the semigroup again, and I get some new function here with this semigroup and a time shifted thing. Now, the nice thing about this is if you notice that this 2s minus t is always less than or equal to s for s, low power mode. So what I wanted to say was notice that 2s minus t is less than or equal to s for s in the interval 0t. So this is actually always adapted. Yeah. So what I could do is I could say, fine, I'm just going to treat, well, what happens if I call this f tilde, this little part here? Well, this is just Duhamel's again applied to this f tilde, right? So I have these two different equations, one with f and one with f tilde, that don't agree anywhere except at time capital T. At time capital T, these two solutions agree. I've now made this more regular. So they agree at time t, but they don't necessarily agree at time t less than capital T. But ft is more regular than f on 0t. And in fact, it has exactly that extra derivative that I need to get the smoothing. So it exactly satisfies the bounds I need. So now I can apply Gersanov and I can actually apply to get time t. Okay. So right, so I can look at this. I have to look at this being an L2. That's just this, which turned back into this, which was just the integral I did before and convinced you that would have been fine. Yeah. So at first it seems like a trick. So let me tell you why it's not a trick. So there's some, right? So I have this u of t, which is equal to this integral from 0 to t of t minus t xx wt plus the integral s ds, right? Okay, and what this really is saying is that there's some linear operator, and what Duhamel's principle says is this linear superposition. I have this initial condition that I'm injecting at time 0. I propagate it forward to time t. I have all these inhomogeneous forcing terms that are injecting impulses in at every time 0 between 0 and t. And what I need to do is I need to push them forward with the Jacobi flow. I need to push them forward with the variational flow. the linearization, the linear equation, 2 times t, and then add them all up. And because it's linear superposition, the effect of all those little impulses can be collected at time t after being properly transported forward with the linearization to get the solution. And that's why variation of constants works. It's linear superposition, right? Okay. What Gersanov says is there's this Brownian motion down here, and at time s, I have a little injection of randomness, of drift, right? And it says, hey, I can just pretend like that was shift the Brownian motion down there and just pretend it was just I used a slightly different realization of noise that had that same shift in it. Right? So I can just turn it into a different realization of Brownian motion and compensate for it. And the problem is that I can't do that at that moment of time because their covariances it's too rough. But the linear superposition says I can either compensate for it instantaneously at the moment it was injected, or I can wait a moment. So what I'm going to do is I'm going to go to time t plus s over 2. And of course, if this was injected here, when I push this forward to time here, I push it forward by the linearization. Okay, so I push forward, if this is r, I push forward kind of going from s to r of this f of s. I push it forward, and now when it's here, I can compensate for it now in terms of the Brownian motion. Okay? But because I pushed it forward a little bit using the heat semigroup, I've smoothed it. And all these integration tricks, the only thing you have to worry about is as you come to this singularity. So I've taken a full time interval singularity, and I've turned it into a singularity just at the endpoint, right? That's what semigroup theory does. That's why semigroup theory improves regularity, right? Because now I just have an integrability condition as I approach the final time, and I lose my regularization, right? This is just classic semigroup theory, right? So I take this, I push it forward, I go half the way, and I push it half the way, all the way to the end. Yeah? This makes sense? Yeah, I gotta turn my screen back on. I talked too long. All right. Are we good? Am I back? Am I live? No, it doesn't look like it. How'd that happen? All right, let me try again. Sorry, let me try one more time. No, it's fine. It's just operator error, I'm sure. We should all be really good at this, but somehow I managed to blow it. All right, great. So here we go. Go away. All right. So I call this time shifted Gersanov. So I do Gersanov, but I just shift the time, so I get a regularized version. And this lets me prove absolute continuity for burgers at time t, not on path space, but at just at time t, which is nice. Okay, so let's see, how much time do I have? 50, right? So I have 20 minutes left. Okay, so let me go ahead and tell you. So this works for burgers for alpha less than 1/2. Right, because that's when I said my regularity was C 1/2 minus, I guess I called it gamma, minus alpha. So if alpha is less than 1/2, this has positive regularity. Now, of course, the minute I cross over the boundary, below that, I need to use singular PDE theory. I use regularity structures or some kind of controlled pair product stuff. Or in this case, actually, since I have this simple u squared with the derivative outside, it's really kind of the original de Prato-Debuche setting. No, I did it. Oh, you know why? Oh, okay, I understand what's going on. It's because it went into low power mode. I need to turn off low power mode. Because of low power mode, it's like shutting itself down instantly. Whenever I walk away for a minute, it decides to shut itself down. But it's being charged, so that shouldn't be a problem. So I'm just going to share one more time. Sorry about that. So, okay, so let me tell you the following is true. So actually, I think I forgot, whoops, it's not what I wanted to write up. So let me go ahead. So let me just foreshadow a little bit where I am. Let me just put this up. I just want to add a page here for a second. So for alpha less than 1/2 works for burgers. So alpha equals 1 is KPZ. I think this is actually probably written on the next is KPZ. I mean, this is the derivative of KPZ. This is Burgers. So KPZ is usually the Hamilton-Jacobi equations, the derivative of it, but this would correspond to Burgers. And this one we actually know the white noise, but I'll talk about that in a second. But let me just point something else out. If you think about two-dimensional Navier-Stokes, and so let me just write that in vorticity formulation. So Q of T. So I don't write omega. I'm sorry, everyone. You're just gonna have to get over that. It's just I can't bring myself to write. Sorry, I can't bring myself to write. So this is the Biot-Savart kernel dotted with the gradient applied to Q equals new Laplacian Q plus some K to the alpha W dot K T, and I forgot to put in here, and let's just put in complex, let's just put in e to the I K dot X. Okay, and so I'm thinking about X on the torus. And of course, this is the vorticity formulation, so it's necessarily incompressible, and I have the Q dx is 0, so it means 0, okay? So if I take this simple example, I can't, everything I said, I can't actually prove absolutely continuous with respect to the Gaussian measure. So if I erase this, I have another Gaussian measure. I can't prove it's absolutely continuous. But if I make this 1 plus epsilon, so the trick I just showed you for Burgers works for 1 plus epsilon, but it doesn't work at the borderline case, okay? All right, and I don't know how to do it yet. So we're supposed to show open problems, all right? So I can't show that the law of Q of T is absolutely continuous with respect to the law of some Gaussian. Some ideas, but I don't have anything done, and it's, you know, so I conjecture that it's actually not absolutely continuous with respect to like this Gaussian. I think it's not.
If you write this in velocity variables, could you explain just roughly the difference with Burgers? Why is it a problem? Why is the pressure a problem if you're using L2 type spaces?
Not a problem.
So, okay, so what's the problem?
In
Okay,
Burgers,
sorry,
I'm
I
in
forgot
one
that. I
dimension,
always
and
forget.
Navier-Stokes, I'm in 2 dimensions.
Okay, so, right, okay.
All right.
So 1/2 is not 1/2, 1/2 is 1. And,
Yeah,
okay,
it's not
thank
the
you.
pressure. The
Thank you.
problem,
Okay, it's just
the
dimension.
problem is the dimensionality.
So Burgers in 2D, you would be stuck
Yeah,
as well.
I think I'd be similarly stuffed.
Would
I
it
might
be
even-
easier to look at Burgers in 2D or not?
I don't know. I think
Okay.
losing incompressibility makes me sad. Right? There's a lot of integration by particles that I would lose, right? And lose, it'd be less regularizing. So let me tell you. So it's interesting that I can prove this for anything positive. The trick I just showed you works. This time shifted Gaussian and you get the answer that this is true for epsilon positive, but I can't prove when epsilon is 0. There's a related question. It's not as related as I thought initially, but let me explain to you another problem that until recently was also open. So what if I go back to Burgers and I go to negative regularity? So actually Burgers and Navier-Stokes both have some similar behavior. When I take Burgers and I put alpha equals 1, we know what an invariant measure is. If it's exactly that form I wrote, the Gaussian measure is the invariant measure. But if I make the smallest algebraic change to that, if I just change the gradient to the alpha for one term, add a 1 somewhere, it breaks it. And we don't know it's invariant anymore. And there's no way that could change this absolute continuity property. Okay, that's not true. It would change it in this case, I'm sure. But what happens now if we try to do it for singular SPDs, right? So what if we try to do this for alpha greater than, for alpha greater than 1/2? So we're going to have to, I'm not going to go through the whole story about how we have to subtract singularities. We do. We're going to have terms that we're going to have to subtract singularities in kind of what's, you know, in the spirit of Descartes-Debouche and Martin's theory in particular. We're going to have to subtract off singularities here, okay? But maybe let me, for those of you who know that theory, or those of you who've seen enough talks on that theory, so you know the kind of the movie of it. You've seen the movie version of that theory. Recent paper with my graduate student Longshan Su and Marco Romito in Pisa. We were actually able to prove alpha from 1/2 all the way up to just below 1. And it's the same exact phenomenon. KPZ has a lot of the same scaling properties as 2D Navier-Stokes with white noise. And with gradient KPZ, Berger's with gradient white noise has a lot of similar properties to Navier-Stokes, but there's still some differences. I'm not sure they're exactly the same. But let me explain to you what we were able to do here. And maybe it's an interesting idea. So how long do I have? Okay, so I'm going to kind of just show you. I mean, so in a way, these lectures are all about kind of showing these absolute continuity and these measure properties and different ways of showing convergence. So here on this first day, I'm really talking about things like absolute continuity. I'll make some connections to infinitesimal ideas at the end, but let me show you this idea. So we're going to decompose our U into a sum of a whole bunch of sums remainder, okay? Now, a difference from kind of the classical regularity theory ideas is we're going to actually keep noise everywhere that we can. So we're going to also decompose our covariance operator into a sum of a whole bunch of covariance operators, okay? Right, you can decompose a positive definite kernel into a sum of positive definite kernels. And we're going to choose them. So morally speaking, you have to kind of fix the coefficients in front of them, right? So there's some coefficients in front, which I have not put in here. But morally speaking, I'm going to think of the Q stars, so the sequences, they decay to be alpha K, where alpha K is some decreasing sequences of alpha. So this covariance is becoming more and more regular because the powers are going down. Yeah. So this is the rough forcing that I start off with. So these two have the same regularity, but these are all lesser regularities going down. I mean, smoother and smootherness. So once you have an alpha, you pick an n so that this is bigger than alpha. And you notice this asymptotes to 1. So I can't pick alpha equals 1. Alpha has to be strictly less than 1. All right. And then once I have that, I decompose a lot like one does in singular SPD theory, but one keeps a noise now at every single level, all the way down. The nonlinearity, so here kind of like when you do these estimates in singular SPD theory, you often look at how the convolution, what the regularity of the Z term is, because that's often your enemy that you have to worry about, right? So you take that, this is just the linear equation, you plug it in, and now you put it in the nonlinearity. And then at the next level, you add them up, you integrate them in some sense, and then you subtract off what you already used. So this is a telescoping sum if you look carefully, yeah, when you add this up, because my total solution is this, the sum of all the x's. So I'm essentially peeling off. It's a little bit, we are kind of inspired by these ideas where people have separated solutions into a more regular part and a less regular part and controlled them, right? And made use of that. I'm pretty sure Isabel's done that at least once, right? I was certainly inspired, but informed by those ideas, right? Right, so we're increasing regularity as we go down. And as I said before, there's this constant interplay by this being not too irregular relative to the covariance you have. So you can't decrease, this has to decrease at a slow enough, these Qs have to decrease at a slow enough rate, so they're kind of paired with what the additive of the regularity. And what we do, the small technical fact is we do this thing all the way. Remember, I said I'm starting with something which has kind of non-classical regularity. So these things, all these ones up here have Holder regularity, which is negative. But I can decompose this thing all the way down. By the time I get to the R equation, it actually has positive Holder regularity. And so this one's a classical solution. And then I have slightly more tools to get rid of. It turns out the Cameron-Martin theorem works well at the negative regularity, but the Gersanov theorem doesn't work as well in this setting. And so I used the Cameron-Martin theorems up here. And you may say, but this is not deterministic. And you made this big deal, Jonathan, about this being deterministic. But it is deterministic because this only depends on the level above. It's independent of this noise. So if I condition on it's triangular, right? So I can condition on the levels above. And okay, so I'm not going to talk about that. There's a connection if you want me to. Oh no, I will talk about this. Okay, good. Sorry. So what we end up proving is that at each level here, there's a corresponding Z when you remove the noise. And we proved that the law of this condition on kind of the upper triangular part above is absolutely continuous with respect to the law of z at that level. And so we had this kind of ladder of absolute continuities. And so then when we're done, we end up being able to show that the sum of all these are absolutely continuous with the sum of all those. So the same ideas kind of using this time shift to Kirsanov can let us build all the way up to SP, to close to the critical value in SP. There's a second decomposition because somebody's probably going to ask me about this. I'll just tell you, where instead of forcing it with the solution at the previous level, we can actually just take all the singular trees that we'd have to worry about and separate them out into a ladder of singular trees and just feed them in one by one. But let's not. So there's a connection. There's a connection to the tree Ito Duhamel expansion. We use a mixture of Cameron-Martin, and so I won't go into this much, but I kind of wanted to just give you the basic idea. I wanted to give you the basic idea of these things. So I have one last thing I want to tell you before time is up, and I have 8 minutes left, I think. So what I've shown you so far is I've shown you. So I start off saying like, oh, I want to show things like this. So I start off talking about this. I have suddenly switched to showing that the probability, if you will, if you'll let me be slightly starting from x, of this being in some kind of dy was absolutely continuous with respect to the probability of this linearized process being in some dy starting from x. The point is that once you show this, you can actually show that this has the same. You can actually these two are equivalent. These two are equivalent for different x tilde. I actually show these equivalents. So I'm kind of passing through because when I'm in infinite dimensions, all of a sudden I don't have Lebesgue measure. So I'm saying, hey, what if we tried to find a Lebesgue measure for this problem? What if we tried to find that right topology that the PDE has absolute continuity with respect to? Let's find that right topology. And I'm telling you, in all the things I've shown you so far, it's the linearized equation where I remove the nonlinearity. Well, what if, but I told you it broke down at Navier-Stokes and it broke down at critical burgers, right? KPZ. What if I just went ahead and proved this directly? That's asking for less, right? Because I lose a lot of information. I no longer know that it's absolutely continuous with respect to this nice Gaussian measure, and I lose, because here I have all the almost sure properties of this solution field are now the same as this Gaussian field. But if I force Navier-Stokes, then I could show this. Now, this is true for Navier-Stokes and it's true for KPZ. That's the theory. We don't yet know what if there was a Gaussian measure to compare it to. Okay. And so then the question is, how do I approach this slightly differently if I wanted to show the continuity?
Jonathan?
Yeah.
So this iteration procedure doesn't work for 2D Navier-Stokes?
No.
Okay.
It doesn't work. It doesn't even work for super smooth solutions as long as they're. If I take 2D Navier-Stokes, where I wrote that somewhere. I remember writing it. This, as long as this right here, Isabel, is decaying algebraically like that. Like think alpha equal to minus 10 to the 100. Okay, so it's super smooth. It still doesn't work. Can't make sense of it. But the minute I put epsilon here, so it's really critical. It's right on the edge. Being able to prove absolute continuity with respect to the linearization, we can only prove absolute continuity with respect to essentially the invariant measure.
Although if you iterate and iterate and iterate again, then you get positive regularity.
Yeah, but it doesn't. But I don't even. But the point is, I don't need for burgers. Remember, I told you it worked. So when I iterate down, I get positive regularity, and then I can apply the theorem I already have. This doesn't even work for this, okay. Which is sorry. I meant to put the minus. I meant to put the minus up here. No wonder you're confused. 10 to the minus 100, right? So if alpha, so it's super smooth. No, alpha is the exponent.
Just fine with.
Yeah, I know alpha is the exponent. Yeah, I meant to put it where I put it. Sorry, I got confused. Yeah, so it's not a question of regularity, right? I mean, the thing is that the kind of thing we'd like to put here, we'd like to actually have our forcing look like something maybe like e to the minus w dot k, for instance, maybe. Or even just finitely many, even just k. I mean, I always want this, right? Right? I mean, that's super smooth. And so now you'll have no hope, right? So the conversations in my little discussion that I'm having with you, I'm kind of starting from two ends of the conversation. Today, I spent most of my time talking about what happens when I have so much forcing that it acts like finite dimension. And I'm kind of telling you that 2D Navier-Stokes and KPZ are at the end point of that conversation. in many ways, they act like they're in finite dimensions. They have this absolute continuity property. That endpoint, the two endpoints, we don't actually know what the right measure is to make this kind of statement, to say what the comparison measure is. I mean, we can always take the invariant measure here. Turns out that you can always put the invariant measure here. They're always equivalent to the invariant measure if they're in this setting. So you can take that as your measure, but that's not constructive. That doesn't give you any insight into the structure of the invariant measure, right? Whereas in these other problems, I actually get a lot of insight into the structure of the invariant measure because I know what the almost sure solutions look like. I know the fine scale structure of the solutions once I know it's absolutely contained with respect to the Gaussian. Navier-Stokes and KPZ are exactly at the threshold. Now, the other side of the conversation is what happens when I'm forcing only finitely many modes, or I'm forcing with super spatially very smooth forcing, right? Now, I've already told you that I have trouble even with algebraically decaying forcing for Navier-Stokes and Burgers, and there's a whole bunch of equations where what I want to claim is that that's really much more like being hypoelliptic. Even if you force every single mode, it's really like being hypoelliptic. So like, I claim that if I have this forcing here with P to the 100 here, I might as well have put having that or this is the same, right? The properties of it are as if you only had a finitely many forcings, which that's not true in finite dimensions. In finite dimensions, the minute you're elliptic, you're elliptic. It doesn't matter how little noise you have in some direction. You'll instantly get all the benefits of it. All right, so now I've talked about kind of as close as you can come to ellipticity in infinite dimensions, maybe. Now what I'm going to talk about is the other side, kind of when you come back from the hypoelliptic side. And I'm also going to give some indication about how you would prove this, maybe, at these boundary points, because we'll use slightly different methods. How am I doing? Spot on.
Now we did it.
Now, what?
Now we did next time.
Yes, yeah, next time. Correct. Yes, yeah, what I'm going to do next.
Any question in the audience? Maybe I have a little one. So I have trouble to reconcile these two ideas that, okay, if you have well, at some point you said that smoothness does not help, but roughness obviously does not help either.
Easier.
Okay.
No, roughness
does make a
yeah, roughness makes your job much easier. So like proving this property for roughly forced Navier-Stokes is not that hard. And proving this property for roughly forced KPZ is not that hard after you know how to take care of it. I wrote a paper, Melf wrote a paper about it, proving Strongfeller, right? And then, in my case, I wrote it with Martin, which meant that we knew how to take care of all the bad terms. Wrote it with Hendrik knew how to take care of all that, right? So, or you knew too, but yeah. So you have to, so there's difficulty there, but there's not difficulty in the sense of the ergodicity, right? The ergodicity is straightforward in some sense, right? Because you have lots of noise around. The more noise you have, the nicer things are.
Any other question? If not, let's thank Jonathan again.